Chapter 14 Quantum Mechanical Postulates. Section 14.1 Quantum Mechanical Postulate 1. Quantum mechanics is built on 6 quantum mechanical postulates. Postulate 1 states that all particles are probability waves. The probability distribution of a particle in space can be described by the squared modulus of the wave function of the particle, and this wave function is denoted by uppercase Greek letter psi of r and t, where r specifies the position of the particle, t denotes time, and this r is a vector with 3 components, x, y, and z in the 3 dimensions. At time t, the probability of finding a particle within a box with an infinitesimal volume of dx times dy times dz is psi squared dx dy dz. To be more accurate, this is the squared modulus of psi. At any given time t, the integral of the squared modulus of psi times dx dy dz over the entire space is 100%. So we have this equation. This is a triple integral. X, y, and z are from negative infinity to positive infinity. That means we need to integrate over the entire space. And over here, this expression is the probability of finding the particle within a infinitesimal volume of dx times dy times dz at position x, y, and z. The physical meaning of this equation is that the total probability of finding this particle in the entire space is exactly 100% at any given time. The squared modulus of a function is the sum of its real part squared and its imaginary part squared. For example, if the wave function psi can be written as f plus I times g, where I is the square root of -1, then the squared modulus of psi is simply f squared plus g squared. Both f and g are real. But over here, when you look at this entire expression, it's f plus I times g. So f is the real part, I times g is the imaginary part. The modulus of psi is the square root of f squared plus g squared. F and g are also functions of the position of the particle and time. Again, this r is a vector that's used to specify the position of the particle in a 3-dimensional space. The squared modulus can also be obtained by multiplying the complex conjugate of psi and psi. Psi star denotes the complex conjugate of psi. So how do we get the complex conjugate of a function? It's very easy. You just need to find every occurrence of I in that function and replace all this occurrence of I with negative I, and then you will get the complex conjugate. The complex conjugate of a real function is itself, because there's no replacement. For example, when psi is equal to f plus I times g, then we have the complex conjugate equal f minus I times g. All I did was to replace this I with negative I. Again, the squared modulus of a wave function is equal to its complex conjugate multiplied by that function. So if you have a function f plus I times g, its complex conjugate is f minus I times g. We just need to do this multiplication. We have two terms multiplied by two terms, and of course we're going to get four terms. F times f, that's f squared. Negative ig times ig, that's g squared. It's because negative I times I is 1. We also have negative ifg and positive ifg. They cancel. So in the end, the squared modulus of any complex function that can be expressed as f plus ig is simply f squared plus g squared. Again, the two imaginary parts, negative ifg and positive ifg, cancel in the last step of the derivation. Now let's look at one example problem, 14.1.1. Find the complex conjugate and the squared modulus of a complex function cosine x plus I sine x. Cosine x and sine x are real functions, but this sine x is multiplied by I. Therefore, this I sine x is the imaginary part of the complex function. The complex conjugate of this function is cosine x minus I sine x. I only replaced this I with negative I. The squared modulus would be the function times its complex conjugate. And then we have cosine squared, sine x squared, and then we have two more cross terms, I times sine x cosine x, and also negative I sine x cosine x. So in the end, the squared modulus is 1. Another example problem, 14.1.2. Find the complex conjugate of the following complex functions. ln, the logarithm of I times x times y, e to the power of z, 5 minus ix. You may assume x, y, and z are real. And over here, I just replace this I with negative I. E to the power of negative z does not contain I. It's a real function. Therefore, the complex conjugate of this function is itself 5 minus ix. I just need to replace I with negative I. The complex conjugate is simply 5 plus ix. The squared modulus of psi times d tau is the probability of finding the particle in the volume element d tau. D tau is dx, dy, dz located at position r at time t. And this position r is simply a vector with components x, y, and z in the 3 dimensions. The squared modulus of psi is the probability density. That's probability per unit volume within the tau at time t. At any given time, the total probability of finding the particle in the entire space is 100%. Therefore, this triple integral of the squared modulus of psi dx, dy, dz is 1. Here's an example. When a particle is completely confined in a space with a volume of 100 cubic meters, well, we can calculate its average probability density, because we can just divide this 100% by the total volume of the space. The result is 0.01 per cubic meter, or 1% per cubic meter, and that's the average probability density. Again, the average is only 1% per cubic meter, and then we have 100 cubic meters. Therefore, the total is 100%. If the probability density of the particle is evenly distributed in this 100 cubic meter space at all times, then its wave function is simply the square root of probability density. So we'll just take the square root of this, and the wave function can be expressed as 0.1 times meter to the power of -1/2. The unit looks weird, but again, the unit of probability density should be 1 over the unit of volume. The SI unit is 1 over cubic meter. Now the wave function is the square root of the probability density, and therefore its unit should be meter to the power of -1/2. In the three-dimensional world, the SI unit of the quantum mechanical wave functions is always meter to the power of -1/2. When the distribution of the probability density is inhomogeneous, well, we cannot say the probability density is the same in the entire space. Therefore, we have to resort to integral calculus to calculate the probability within a certain interval in space. For example, let's look at a one-dimensional world. If the wave function of a one-dimensional particle is this function, then we have the integral of this function squared dx is 1 over the entire space. That means x is from -infinity to +infinity. C is the normalization constant. The value of C should be chosen so that this integral is exactly 100%. And over here we have an exponential here. The exponential term must be unitless. Now, when the wave function of a particle in the one-dimensional world is the normalization factor times exponential function of -x over 2 meters, and then we have this integral equal to 1. C is the normalization factor, and over here this m denotes meter, not mass. It's meter here. Now let's do some mathematics. We can evaluate this integral, and then this way, and this equation is an even function because we have the absolute value of x here, and then we can rewrite this integral as 2 times this integral with a different lower limit. It's from 0 to infinity. Again, it's just because if you look at this integral, x is from -infinity to +infinity, and the integral from -infinity to 0 is equal to the integral from 0 to +infinity. That's why I have a 2 here and a simpler integral here. We can integrate this. I think we'll get just 1 meter here, so 2 times c squared times 1 meter is just 1. And therefore c squared is 1 over 2 meters, and this normalization factor is 1 over the square root of 2 meters. Now we have this wave function normalized. It's equal to 1 over the square root of 2 meters times e to the power of -x over 2m, and this x is the absolute value of x. If we use this wave function to plug it in here, if we integrate this, the squared modulus of this with respect to x from -infinity to +infinity, we'll be able to get 1. Now, a numerical example 14.1.3. Assuming the wave function of a particle in a one-dimensional world is this, then what's the probability of finding the particle between 1 meter, -1 meter, and 1 meter? And what's the probability of finding the particle between -infinity and -1 meter? So we can simply just integrate the probability dx times dx. We just need to use this lower limit and upper limit for the integral. We can evaluate this integral, and this is just mathematical trivia, really easy to do. We get 1 minus e to the power of negative 1 here. The probability is 63%. So if we have this wave function, the probability of finding the particle between negative 1 meter to positive 1 meter is 63%. So there is still 37% chance outside this range. How do we compute the probability of finding the particle between negative infinity and negative 1? Well, again, outside the range from negative 1 meter to positive 1 meter, we have a probability of 1 minus 0.632. And because the probability is a even function of x, so you can see this is a even function of x, we just need to divide this by 2, and then we get 18.4% of finding the particle between negative infinity to negative 1 meter. Also, the probability of finding the particle between positive 1 meter and positive infinity is also 18.4%. So we have 3 ranges. Below 1 meter, the probability is 18.4%. Between negative 1 meter and 1 meter, it's 0.632 or 63%. Between 1 meter and infinity, again 18.4% due to the symmetry. Postulate 1 states that the squared modulus of the quantum mechanical wave function is the probability density of the particle. It also states that the wave function must be single valued, continuous, and finite everywhere in space. So let's look at 3 examples. This is a wave function, but not a QM wave function. This is not a QM wave function either. The third one, again, not a legitimate quantum mechanical wave function. And they are not quantum mechanical wave functions for different reasons. This one, psi is not single valued. So if I have x here, I got 2 different values for psi, and that's a violation to postulate 1. This wave function, well, this is single valued, but it's not continuous right here. This one is single valued and it's continuous, but it's not finite. As x approaches negative infinity, psi approaches infinity. As x approaches infinity, psi also approaches infinity. Make sure this psi is always finite everywhere, even if x approaches infinity or negative infinity. The essence of postulate 1 is that particles are waves and waves are particles. For each particle, we can use a wave function to describe it. The wave-particle duality is supported by 2 experiments. The first experiment is the double slit diffraction of electrons that proves electrons are waves. The second experiment is the photoelectric effect experiment that proves photons are particles. Now let's look at the double slit diffraction pattern of electrons. If we have an electron gun that shoots electrons, allow the electrons to pass 2 slits, and then we'll observe the interference pattern of waves, the same as water waves. So it can be, well, you may imagine this is water waves, you may imagine this is light waves, but anyway, the interference between electrons create this kind of pattern with the brightest stripe in the middle, and then, well, the lightest, and then brightest, and then the lightest. So we get this kind of patterns because electrons are waves, and waves can interfere with each other. We have two wavefronts from the two slits, and we can have constructive interference and destructive interference. When we have constructive interference between the two electron waves, we see a really bright spot in the middle. But when they cancel, because they are out of phase, you see the lightest stripes. The photoelectric effect experiment proves light consists of individual particles, and those particles are called photons, and each photon is a particle of light. When light is shed on the surface of a metal, an electron on the metal surface may absorb a photon and be ejected. If the energy of the photon is greater than the work function of the metal, the work function is the minimum energy required to eject an electron from a piece of solid. The work function is similar to the ionization energy. The difference is small. Ionization energy is the minimum amount of energy required to eject an electron from an atom. The work function is the minimum amount of energy required to eject an electron from a piece of solid that consists of many atoms. The kinetic energy of the ejected electron is the energy of the photon minus the work function. So the electron needs at least this much energy to escape, and if it can escape, the kinetic energy of the electron that escapes from the metal is equal to the total energy it gets from the photon, which is h nu, minus the minimum amount of energy required for the electron to be ejected. Therefore, the work function can be calculated using this equation, h nu minus the kinetic energy of the photon. The work function of the metal in this diagram can be calculated. Let's do some calculation. So we have this kinetic energy. Well, this is speed, but using half mv squared, we can get the kinetic energy of this ejected electron. And also we have the wavelengths here, so we can compute the energy of the photon. It's given here, it's 3.1 electron volt. You can double check this number. So we have 3.1 electron volt minus the kinetic energy of this electron. We'll get the work function. We can use this data as well. So we have the energy of the photon, 2.25 electron volts. We can calculate the kinetic energy of the electron, which 1/2 times the mass of the electron times its speed. And then we take the difference between h nu, the energy of the photon, in this case 2.25 electron volts, and then minus 1/2 times the mass of the electron times the speed squared. We'll get the wave function for this metal. Now let's look at one example problem, 14.1.4. We can also plot the kinetic energy of the ejected electrons versus the frequency of the photon in an Excel spreadsheet and determine the Planck constant. Here is how. Let's say we have two data points. We have the wavelengths of the photon, and then we calculate the frequencies of the photon. We have the speed of the ejected electron, and then we can compute the kinetic energy of the ejected electron. Now what do we do? Kinetic energy is a linear function of frequency. The slope is h. The intercept is negative w. If we plot kinetic energy versus frequency, so it's pretty simple. Make a graph of kinetic energy of the ejected electron versus the frequency of the photon. The slope is going to be the Planck constant, and negative w is going to be the intercept. Now again, let's look at this example problem. We have kinetic energy here, we have frequency here. We make a graph, we do linear regression, we determine the slope. Slope is 6.67 times 10 to the power negative 34. What's the unit? Joule over Hertz. And this is simply the Planck constant. And over here we have the intercept, a negative intercept. This is actually negative work function. So immediately we know the work function is 3.24 times 10 to the power negative 19 joule. So we have learned that particles are waves, waves are particles. Two examples: electrons, we know they are particles, but they are also waves. Light, we know light is a wave, but light consists of particles as well. Each particle is a photon. In 1924, de Broglie proposed an equation that quantified the wave-particle duality. The equation is simple. Lambda is h over p. Lambda is the wavelength of a particle. P is the momentum of the particle. H is the Planck constant. But over here, make sure that this P is the unsigned magnitude of P, or the absolute value of P. This is to avoid getting a negative lambda. Although particles are also waves, it's impossible to observe the wave-like properties of a macroscopic object. Why is that? Very simple. A macroscopic object is also a wave, but its wavelength is extremely small. It's impossible to measure. On the other hand, the wavelength of a very light particle, such as an electron, can be much more easily measured. Now let's look at one numerical example problem, 14.1.5. Calculate the wavelength of a football that flies at 20 meters per second. A typical football weighs 0.4 kilograms. So lambda is h over p, p is mv. We plug in the numbers. Well, the wavelength of this football is 7.9 times 10 to the power negative 35 meters. We won't be able to observe such a small wavelength. The smallest length we can ever measure is 10 to the power of negative 18, and this wavelength is much smaller than this threshold. We simply cannot measure or detect the wavelength of the football. It's too heavy. Now let's look at another numerical example problem. This time we'll calculate the wavelength of an electron that moves at 2 million meters per second. The mass of the electron is 9 times 10 to the power negative 31 kilogram. We plug in the numbers h, m, and v. We get 3.6 angstroms, or 0.36 nanometers. And it's fairly easy for scientists to measure a wavelength like this. Now we just showed that all particles are waves. It's just very difficult to measure the wavelength of a macroscopic object such as football, but it's easy to measure the wavelength of an electron. Like electrons, photons are also waves and particles. So we can compute the mass of a photon as well. We know the rest mass of photon is 0, but photons move. They move at the speed of light. And when a photon moves at the speed of light, it has a non-zero mass. Its moving mass can be predicted using the Boyle's equation. Again, the information we have is lambda, 500 nanometers. Now we're going to use this equation. Lambda is h over p, and the momentum is mass times the speed. So the mass is equal to h over lambda v from this equation. We plug in h, the Planck constant, lambda, the wavelength, the speed of light. We get 4.4 times 10 to the power of negative 36 kilogram. So a moving photon with a wavelength of 500 nanometers has a moving mass, which is 4.4 times 10 to the power of negative 36 kilograms. Planck introduced the term quantum in quantum mechanics by showing that the energies of the photons emitted by a heated object are quantized. A heated enclosed cavity emits electromagnetic waves, and it's so-called black body radiation because the design of the apparatus makes sure light can hardly escape from the cavity. Electromagnetic theory predicts that the spectral density of the photons inside this cavity can be calculated this way. Rho is 8 pi nu squared over c cubed multiplied by the average oscillation energy of the atoms inside this cavity. Now what is rho? Rho is the intensity of the emitted waves divided by the range of the frequency. Alright, for example, if you have intensity of a photon between 10 to the power of 14 Hertz and 10 to the power of 15 Hertz, you just need to use the intensity divided by 10 to the power of 15 minus 10 to the power of 14. Now let's look at some classical mechanics predictions. Classical mechanics predicts that the oscillation energy of the atoms inside the cavity is kBt on average. This is based on an assumption that energy is continuous. That means the energy spacings between any two adjacent oscillation energy levels should be infinitesimal. And therefore we have this equation. We plug in this oscillation energy equals kBt over here. We get this expression. It shows this spectral density rho is proportional to nu squared or frequency squared. That means as the frequency increases, rho increases. However, that's not the case when we do the experiments. There are mismatches. Now let's look at some experiments that were conducted to plot this spectral density rho versus nu squared. When the frequencies are low, we have this 8. Well, we have this equation, and how low should this frequency be when we have this proportionality? Well, the criterion is this: nu should be low enough that h nu is much smaller than kBt. And then we have the spectral density proportional to the frequency squared. However, experimentally also we found that when the frequencies are really high, so maybe this h nu can be much greater than kBt, well, we found rho is equal to a pi nu squared over c squared times the average oscillation energy, and that approaches zero. So there's some disagreement. Classical mechanics predicts that the spectral density is always proportional to nu squared. In quantum mechanics, rho is proportional to nu squared only when the frequencies of the oscillation of the atoms are very low. What if you have high frequencies? Well, in that case, the spectral density approaches zero. Now let's look at a graph over here. The graph is intensity versus wavelength. So when you have a larger wavelength, you have a small frequency. When you have a small wavelength, you have a large frequency. So in this region, you can tell that the intensity decreases as the wavelength increases. But in this region, you can see intensity increases as the wavelength increases. So now let's think about this. When the wavelength approaches zero, its frequency approaches infinity. So that's a really high frequency scenario. And this rho is supposed to be approaching zero. So over here, these three curves are approaching zero when the wavelength is small. Now when the wavelength is large, we'll have a smaller frequency. And then we should use this equation to make predictions. Since we have low frequency, h nu is smaller than kBt, the spectral density rho is equal to nu squared over c squared times kBt. Alright? And this rho is just proportional to nu squared. So now let's look at this example again. There's a mismatch between the experiments and the prediction from classical mechanics, and it's called ultraviolet catastrophe because the mismatch is serious in the UV range. The mismatch is less serious in the visible range. The mismatch can be almost neglected in the infrared range. So what causes this ultraviolet catastrophe? So what happens to the relationship between the spectral density and the wavelengths? Well, the thing is, in classical mechanics, the oscillation energy levels are assumed to be continuous. Based on this assumption, we can derive the oscillation energy to be kBt. That's doable. But Planck proposed that energy is quantized in this black body container or cavity. The only allowed energy values are in 1 times h nu, 2 times h nu, 3 times h nu, etc. And based on this assumption, Planck derived this equation. He said if the frequency is high in the UV range, the oscillation energy is equal to h nu divided by e to the power h nu over kBt minus 1. Well, apparently this oscillation energy is not just kBt. So over here, classical mechanics, it's kBt. Over here, well, definitely it's not kBt. So Planck proposed a different expression for the oscillation energy. and the spectral density is equal to a pi nu squared over c squared times the oscillation energy. So we have this expression. What if nu approaches 0? Well, in that case, the exponential function minus 1 is approaching h nu over kBt. So you just need to know the Maclaurin expansion for the exponential function. The Maclaurin expansion of e to the power of delta is simply 1 plus delta squared over 2 factorial plus delta cubed over 3 factorial, etc. When delta is small, we can keep only the first two terms, 1 plus delta. And therefore, this equation, e to the power of h nu over kBt minus 1, is simply h nu over kBt, as long as nu is small enough. And now we can further simplify the expression of rho. You can see rho is now proportional to kBt when the frequency is low. So at a low frequency, the classical mechanics holds. The oscillation energy is proportional to kBt. But what if we have a high frequency? When we have a high frequency, now let's look at this expression again. When we have a high frequency where h nu is much greater than kBt, what will happen here? Well, this part is going to be infinity. Alright, so e to the power of h nu over kBt will be approaching infinity. And on top, I think we have nu to the power of 3. It also approaches infinity. However, the exponential function approaches infinity faster than the polynomial functions. So that means when h nu is much greater than kBt, well, we're gonna just have this rho approaches 0, because although the top and the bottom both approach infinity, the bottom exponential function approaches infinity much faster than this nu cubed. We can also use this expression to make a prediction about when this rho reaches maximum. Well, it's pretty simple. We just need to take the first derivative of this with respect to the frequency nu, and then we can set d rho, this is d rho, the exact differential of this with respect to frequency is 0. And we can do variable substitution to make the calculation a little easier. If we assume h nu over kBt is denoted by x, well, then first derivative of this rho with respect to nu is gonna be computed given this expression, and setting this first derivative to 0, we'll get e to the power of negative x equals 1 minus x over 2. Again, x denotes h nu over kBt. Solving this equation, we get x is 1.6. So you can see the maximum here, here, and here. You'll see at the maximum h nu is 1.6 kBt. So when you have a higher temperature, well, you'll have a larger frequency. Alright, higher temperature from 3000 to 4000 to 5000. You can see lambda decreases, and that means this nu increases. Alright, for the maximum point here, here, and here. At this 3 points, h nu should be 1.6 times kBt.